so then people can just kind of just whatever the mics are picking up, but it's not much at this time. It's just so that they can like, if they want to watch the talk, you start it. And then when you're done, ask you to confirm you want to end it. And you do. The live streaming part is pretty self-explanatory once you know what the buttons are. Yeah. But yeah, and then just make sure I invite the speaker about 5 minutes before, and I will come and get it after the talk before the question and answer period. And I just usually turn those off so it's not yeah.
Oh, okay. Like during the talk?
Yeah, because this is just the display, so it doesn't
matter. Oh, yeah. It's like smart.
Yeah, to see yourself. Yeah.
Okay.
Yeah. Not too bad.
Sometimes when I have free time, like we all do this, pick up a little bit before everybody comes, like put the dishes away.
Okay.
You know. But sometimes I don't have time. Yeah, it looks pretty presentable in here.
Yeah, and this is all your space. And we have some water also behind
There's knives and
yours.
stuff from Friday I watched.
This works to advance the slides, and there's like a pointer. It's really
We have the reading
light
stuff.
though, so and also
That's
people on the live stream won't be able to see it.
Somebody said.
And then just about 5 minutes before, I'll give you. We have a lavalier mic.
And then afterwards.
Once I turn that on, then anything you say will be live streamed. Yeah. Oh, and we will not live stream the Q&A. Just the
Reservation portal things.
Okay.
Because I think he already, when I put in his phone number, it didn't recognize my email address, so he had to make that one himself. But I'll ask him before he's going to go to dinner next Tuesday and make the reservation there. And one of the venues around here, some of the nicer evenings. So we'd like to get those. Heads up. We're really funny about
I
that.
try not to touch too many things in there.
That's coffee party, but, yeah, that's why I do coffee party. If I don't get it from my granddaughters, they're all sniffling yesterday.
We're all like,
Mira came over,
they more
Saturday night, we didn't go to church because she was sniffling and hacking, and she slept with me, so
Oh,
I'm gonna take my
especially
vitamins
you
and
because you're
everything,
yeah.
and then whatever this,
What we don't need
my
is you
son's
getting
house
on a
and
plane with a
Ruby's
fever.
running that. She's
We'll
three.
put a
I
bunch
don't
on
know
the
if they
news.
let me. Yeah, they won't let me
But
first.
we'll see
I'm
your
gonna
face
take
on
my
the
word.
on the
Yeah.
news.
but
I've been
How
how about you?
any lunchtime talks that I wanted to.
Oh. Yeah. Oh my. Okay. I got to do
The
some
longer
of these
here,
things while
we're
I
here,
fresh
the
my
longer,
head.
the more you get immune to it.
I know. Yeah. When I started.
You hear what Carolyn said? So when you touch, like we're all so fun. I'm becoming terrible.
Well, you guys
need
need
to get some water.
incubate me or like quarantine me.
Oh,
when I come
you're not
back.
coming in. You're working from home for 2 weeks. I won't be
I'm
here.
going to Singapore.
Oh, yeah. I heard that.
Yeah.
I'll know when I get an email. I'll see if it's sent. Can you come back to work? I'm like,
Oh, sorry.
but you won't know. No, and sometimes we get sick after the fellows come. Because they bring in germs and colds and things. Good morning, good afternoon.
How are you? I'm sorry I couldn't make it right, but I had to go to my
Physical therapist.
Oh.
So at least,
Yeah.
I was doing
Oh,
something positive.
yeah, so.
What was brought to this?
Oh, that's okay. It was very well. Gave me a number and I didn't have to do
Fast track.
that.
I've been there for 6 weeks. So,
I'll be around another week.
it worked, but it was sort of weird.
Oh, how are you?
Yeah,
So, John,
starts like close.
it started in on like swimmingly. And then somebody said, you seen this book?
And you're like, pulling
Oh,
it in.
so there's so much overlap. I think I
Uh,
have to let it go.
yeah. So, which version of the book you're writing? You're writing the technical one or the gentle one or
The late person version
Someone-
has been done.
but not that one?
No, actually, I would do it slightly differently, but there's so much overlap. Chapter topics is very similar. And he's
always a good time.
the top guy. Yeah.
I always make sure we have Captain Calvin here.
So,
No.
yeah, I know.
Yeah, well, this is what happens when you work on interesting stuff that other people like to think about too. I've managed to build a career by avoiding that.
It's a different strategy.
It works. I mean, I can just move at a very slow pace and nothing, you know.
Yeah, I have been thinking, why hasn't somebody done this already?
Yeah, I know.
But I should have been that person to do it like 3 years ago.
What I normally say, anything that's completely obvious has already been done.
Yeah.
Right? It's always the way it is in research. The idea that you just get easily and, oh yeah, let's do this. Yeah, someone's already done it. It's the one where you think,
So I think I have to go back to my first plan, the
Yeah.
one that was frustrating me. It's just meant to be,
Unless-
meant not to be.
unless you almost can be the two-tier one where you've got, you know, if you
Yeah.
track it, well, you have the simpler track and the more complicated track, and then you can, you know, so you kind of,
Feedback or maybe 2 tiers in the
I don't know why. I'm just putting this up.
We might were like full and very.
Clara.
I'm leaving.
Clara. No,
I think so too.
good.
We were playing on the time.
You know, I could make another really inappropriate joke about it, but I'll tell you over here. Remind me. I'm hearing the worst.
Okay, so you should say.
Yeah, it'd be like Friday evening.
Hi.
No, and Saturday.
Yes.
You would have to. Yeah.
You did the email.
Even if it was fun.
It was fun.
You went for an upgrade?
We were walking and
No, that was I was back on the way here. For me,
Yeah.
it's- yeah, that's what I meant with an upgrade. Yeah. Well, I can think of it this way.
Oh.
Yeah.
Are you a potential job looker out here?
She already did.
I'm looking for somebody. How long are you sticking
Hey,
around Pittsburgh?
I used to
Good.
and then my side.
Here in Texas?
Oh.
The beginning of it or the end of it? Oh, okay. Well, I'm gonna invite a bunch
Sorry,
of
watch it.
house sitter, dog sitters. We need somebody from May 5th to the 20th. So we may break it into different groups if people don't want to do that. I'm gonna have a dog visitation. That looks good. That looks better than my apple.
You know, I find the apple and bagel option is.
Well, I teach a seminar.
They're done. Now, how are you doing?
I can't.
Very bad for the
No
internet.
interest.
I never think what happened to you.
You got a concussion?
Very minor one. Okay. Went down, back to the bottom of the other hill.
But you went down your leg.
Yeah, definitely. So I didn't lose consciousness, but I raised my arm.
Oh,
yeah.
where was the
Rotator cuff injury?
What's that?
Rotator cuff injury.
No, ski accident.
If I'm going like this.
So,
Well, if you just give me the instructions.
yeah.
Yeah. It's the
So,
opposite.
anyway,
It's
you
like
just
a-
It also was.
Yeah. So now it's on it. the room and also to the live stream. It's caught like a little bit more, so I would recommend putting it down more like here if you know you're not a quiet speaker, because it's been catching like if people sigh or like you know what I mean, where it projects kind of loudly. I don't know. Well, if you make any incidental noises, having it a little further away will help. And then
I know.
so I'll just
I know, but I do phone on the regular basis. Most of the phones are completely wrong. Yeah, completely fine. But my arm is bad. I'm gonna implement tomorrow.
I was about to ask you about that.
I did that too.
Yeah.
There was some people that were bad.
Okay.
That's when I heard about my arm. It used to be like 5 years.
I don't know what I thought you were saying. The thing is, in like urban studies, whatever, the operationalize it in a certain way.
Oh,
I do.
So from like the tests, when they give a temperature sense, then they measure if.
Anyway, it's about you.
That's like the measure of like. Yeah, that's right.
And not
I think that picture's also basically, I mean, also my really trying to get.
Are you okay?
That's the view I want.
Oh, anyway, I don't agree.
It's very, it's not what we think.
Yes.
I don't think that really helps or anything.
I have so much. How was your trip? Very good.
So that's the ultimate. Oh, that's good. That's interesting.
How did you decide what to do?
Ah, you're back.
It's true.
When did you get back?
It's true, we do. When is it? None of them are so great that we can't just having a conversation. Temporary It was good. He didn't wake me up in the middle of the night. No, it was more like 8:30.
Yeah, I think so.
And then we let him out. And then just like closed the door and it was fine. He slept for an hour. He's a lot more pliable in Seattle. No, that part is he's not. But if he gets where you're like, I need to snack.
I get this enthusiasm.
Yeah, I wanted to lunch talk and let you know about what's happening in the coming days. There is no lunch talk on Friday, but Fletcher is giving the Richard Prize lecture on human progress at 2 p.m. on the 10th floor. You're all invited to come to Philip's lecture. The next lunch talk at the center is given by Philip Abbas. Philip right there, who's going to be talking about a generalized patchwork approach to scientific concepts, a very Pittsburgh-like talk, and we're looking forward to that talk. But today, it's my pleasure to introduce Sam Fletcher from the University of Minnesota. Sam is an assistant professor, as I said, in the Department of Philosophy at the University of Minnesota. He is a member of the Minnesota Center for Philosophy of Science. An external member of the Munich Center for Mathematical Philosophy. As you probably all know, he worked in philosophy of physics, but also philosophy of statistics. And today the talk is going to be in the philosophy of statistics. He developed his interest, I don't know, maybe recently or for a long time.
I'll talk about
okay. Maybe in connection to application prices. Anyway, that's the way I've come across his work. And he recently was awarded the title of a Matt Knight Land Grant Professor at the University of Minnesota for the next year. Congratulations. And today we're going to hear about secret testing.
Thank you for your kind introduction. The genesis of my interest in philosophy of statistics actually went back to my undergraduate days studying physics. So I was working on an independent project on the history and development of neutrino physics. And one of the interesting topics in that subject had to do with the shifting sands of support for different hypotheses about the nature of neutrinos. These shifting sands, to illustrate one example, consisted of controversial experiments that seemed to contradict past data. Then when a new experiment was conducted, that old experiment, the contradictory one, was discarded into the waste bin. Now, with someone who hadn't had a background in statistics, I thought, well, I must not be understanding why that's a legitimate move, throwing away the data that's not compatible with your hypothesis. And so I resolved when I went to graduate school to try to understand a little bit more about how statistics and experimental particle physics works. But in attempting to do that, I needed to understand statistics better and found ultimately the topics there to be of intrinsic interest in addition to their applied interest in understanding experimental practice in science. So the topic that I want to talk about today is a topic about the foundations of classical statistics, in particular classical statistical testing. Now, like with many scientific disciplines, classical statistics has been formed and developed by many people, but there's many people who think that there's few people who are quite central to classical statistics. The work of the English scientist Ronald A. Fisher, the Polish mathematician Jerzy Neyman, and another English statistician Igor Tosin, working together, developing ideas in conversation with one another that eventually became the sources of the ideas that are used in classical statistical testing. Now, despite this prominence, or maybe actually, I think it might depend on your view of things, whether it's a despite or not, philosophers have been unkind to classical statistics. So here is a representative but forceful quote from Housen and Urbach's popular book. In the introduction, they write, "It's fair to say that their methodologies," referring to the folks I mentioned before, "especially those connected with significance testing and estimation, which comprise the bulk of so-called classical methods of statistical inference, have achieved preeminence in the field and become standards of correctness with many scientists. In the ensuing chapters, we shall show that these classical methods are in fact intellectually quite indefensible and do not deserve their social success." There's two important things about this quotation that I want to draw out. One is that it's representative in the sense that most philosophical work done on statistics has shied away from trying to develop or provide a foundation for classical statistics. The reason for this is basically that it crumbles under withering criticism. Now, there's another feature, though, that I want to point out, which is that House and Urbach say that the primary success of classical statistics is social, it's popular. I think this is quite misleading. To give you a few examples, take one of Fisher's monographs, Statistical Methods for Research Workers, which went through 14 editions between 1925 and 1970, last, of course, posthumous, and has received, depending on how you count, at least over 25,000 citations. Now, it strains credulity to think that the reason for this is that they are popular, merely so, but not because of any other sort of criterion of success they might garner. In fact, they have been used by scientists because they are absolutely, unquestionably, enormously successful, despite the problems that Hausen and Urbach are pointing out. So I think it behooves philosophers of science who are interested in understanding the foundations of scientific methodology to, along with their criticisms of a particular methodology, try to understand the reasons for its success. So what I'd like to do, so maybe I can give you another example. This is a quotation from Frank Yates in an article in 1951. He writes, "It is now 25 years since R.A. Fisher's Statistical Methods for Research Workers was first published. These 25 years have seen a complete revolution in the statistical methods employed in scientific research, a revolution which can be directly attributed to the ideas contained in this book, and which has spread in ever-widening circles until there is no field of statistics in which the influence of Fisherian ideas is not profoundly felt." And this is only in 1951. Now, to be fair, Yates was the successor of Fisher at the Roehampton Experimental Station. So we might take this as being maybe not exaggerated, but definitely accentuating the positive. But I did want to take it as evidence that the success of classical statistics is not merely due to the opinion or social popularity of the methods, but due to their actual success on criteria that scientists care about. Now, one of the folks who has defended classical statistics within the philosophical community is Deborah Mayo. Now, for several decades, she's advocated her own ideas about how we should understand classical statistics in this methodology that she calls severe testing. Here's her 96 book, and here's her most recent book, Statistical Inferences, Severe Testing. Now, despite Mayo's work trying to give a defense of classical statistical methods, testing in particular, or at least her interpretation of them, not many have followed in her path. I think there's a few reasons for this that are captured very succinctly by this interesting quote from the late statistician George Casella. He writes, engaging with her work in an edited volume, Mayo outlines a framework of inquiry that is compelling in its ideas, frustrating in its vagueness, and unworkable in its rigidity. Let me unpack a little bit what I think Casella means by this. So compelling in its ideas, I think he means that severe testing, as Mayo understands it, really does advance new concepts for solving some of classical statistics problems. By frustrating in its vagueness, I take it to mean that Mayo's never provided a clear mathematical formulation of what severe testing is supposed to be. This makes it difficult to communicate with mathematically inclined statisticians and other scientists. Unworkable in its rigidity. The only example that has been applied to is one particular classical statistical test, the one-sided z-test. And for those of you familiar with classical statistical testing, this is about as simple as it can get. So we would like to know, how can this methodology, such as it is perhaps, be applied to more types of testing of interest? So that's what my goal in this project is to develop a mathematical framework for explicating severe testing. with any statistical test. And I mean explicate here rather than analyze. I do have to take some modifications of her ideas. Second, to justify how that framework quantifies evidence for and evidence against simple and composite statistical hypotheses. One of the main difficulties with classical statistical testing is its lack of a clear ability to quantify evidence for a hypothesis rather than just evidence against a hypothesis. I'll talk a little bit more about that in a little bit. Another goal, which I may not get to today, but it's a part of the general project, is to sketch a concomitant logic for statistical inference. That is to say, how statements about accepted and rejected propositions cohere together and inference rules for that. And then finally, which is, I think, the most important thing that I want to do today, is appeal to your expertise on some open problems. I'm just going to have some brute lists at the end of questions that I don't know how to answer that are, I think, really important for this project. So before I go on to that, I want to describe a few things that I'm not doing here. I'm not engaging in an exegetical project today, either of Mayo or Fisher or Neyman or Pearson. I think that project is important, but it's not the one that I'm engaging in today. Another is that I don't take this particular project to be another volley in the statistics wars or about the interpretation of probability. I'm going to set those sorts of issues aside. And finally, I don't take that anything that I'm going to be working on in this project to be solving any of the what are sometimes called cognitive problems of applied statistics. What I mean about this is the difficulties in getting folks who apply statistical methods to understand their meaning and significance. Right? There's a lot of important statistical work on making applied statistics more user-friendly and interpretable. That's also important, but it's also not what my project is today. Okay, so here's an outline for what I would like to talk about. I'm going to review testing a la Fisher and Neyman Pearson in a certain sort of fashion. Then I'm going to talk about severe testing, how it takes ideas from those two and puts them together into a kind of a confirmation theory. What I mean by that is that a theory which assigns quantitative measures of support for and against particular hypotheses. I have a section here about going towards the logic for statistical inference. What I mean again is here how statements about acceptance and rejecting and holding one's judgment in advance cohere with logical inference rules. Depending on how time goes, I might skip that section, but I can come back to it if you'd like to do that. And then, as I said, just this brute section of open problems, questions that I don't know how to answer yet, that I'd like to, in particular, ask you all about to see if you have any ideas. Okay, so let's get started then on this first section, testing Fisher and Neyman Pearson. Let's start with some preliminaries. So first, we're going to start off with a set of possible data sets. I'm going to represent this by this curly X. These are going to consist in all the possible recorded outcomes of a scientific study in question. So, for example, suppose that you're studying the heights, right, of people from a population, and you have a plan that you're going to select any of them. Then X is going to consist of all of the different n tuples of positive numbers. You have some measuring apparatus, of course, and a particular plan for how you sample them. Those are extremely important parts of the research design, but they're not represented in this particular mathematical object. Okay. So next, in addition to data, we also have hypotheses, statistical hypotheses. Informally, you can understand these as the possible states in which one is considering the world to be. These need not be fine-grained. These are states that describe the different probabilities that you want to assign to different types of outcomes in the data. So formally, we can distinguish between two types of hypotheses. First, simple statistical hypotheses. So each of these is going to represent one possible state of the world. Formally, what it's going to do is it's going to assign a probability distribution to all the possible different data sets that you can have. So in general, the different simple statistical hypotheses are going to be mutually exclusive, but they're not in general going to be exhaustive. In practice, you don't always consider all possible statistical hypotheses, only some selected class. So the second type of hypothesis are simply going to be composites of these. So logically, you can think of these as certain disjunctions over simple statistical hypotheses, or mathematically as certain sets of simple statistical hypotheses, subsets of this large space that we're considering. I say certain here because we have to think about certain measurability and decidability questions when we talk about arbitrary subsets. But none of that really is important for what I want to talk about. Okay, so we've got possible data and we have hypotheses, assignments of different probability distributions that we might have to the data. So here's an example of a simple statistical hypothesis. The height of Dutch men is normally distributed with a mean of 6 feet and a standard deviation of 0.3 feet. I learned recently this is not too far off from the truth. An example of a composite statistical hypothesis would be that the height of Dutch women is normally distributed with mean between 5.4 feet and 5.6 feet and standard deviation of 0.2 feet. So we might represent these different situations graphically like this. So here, the blue is the one simple statistical hypothesis that I mentioned. You can see here that we've got a nice bell-shaped curve centered on 6. So here, x, right, is feet. Now, when it comes to composite statistical hypotheses, it's sometimes difficult to represent them all in a graph like this. So I've just selected 3 for you. 3 simple statistical hypotheses that are part of that composite statistical hypothesis. The simple ones that the mean for Dutch women are their heights are 5.4, 5.5, and 5.6 feet. So what's important here is that each distribution, probability distribution, each curve in these sorts of graphs represents a statistical hypothesis. Now, what that means is that depending on the complexity of the space of statistical hypotheses, we could have all sorts of plots and distributions that we could draw out here. Okay, cool. So what's the next part? So in addition to data and hypotheses, we also want to have tests of these hypotheses. So informally, a testing criterion is going to measure comparatively how well data cohere with or align with or are compatible with a certain hypothesis. These different words are kind of used synonymously. They're indicated a little bit more in a formal manner. So what we have is a random variable for those of you who are familiar with the terminology. And in this case, what we can think of it as a map, a function that takes in data and it takes in a statistical hypothesis. And it's going to map it to another space that's going to have an order structure on it. What I mean by an order structure is something like one of these greater than signs that takes all of the different data and aligns them with how compatible that they are from the data. So the one data set is going to be larger than another in this order, just in case it's going to be less compatible than the one that's smaller with respect to the particular statistical hypothesis data. So let me give you an example here. So in this particular case, right, a very natural test criterion would be a particular function that takes the value of the data that we collected. It could be, for example, the mean of the sample of folks whose heights we sampled. We subtract from it the mean of the proposed hypothesis. So for example, if they were Dutch men, this would be 6 feet, right? We divide it by the standard deviation, say 0.2 feet, and we get a number, z. Now this particular number, right, is then going to be ordered in magnitude. The larger the values of z, the more and more the data x, the less and less they cohere with the hypothesis. So what that means is that data that's very close to the mean, towards the top, located in the place where you see that the top bump in the distribution is the data that coheres very well with the hypothesis. And as you get more towards the edges, the data cohere less and less with the hypothesis. The idea is supposed to be that the less the data cohere with the hypothesis, the more evidence that data provide against that hypothesis. Okay. Now, in addition to that strict ordering, that ordinal scale way of describing how some data are more or less compatible, we can also give a quantity, quantify how much they're incompatible. And a typical way of doing that, and the one that we're going to be focusing on, is something called the p-value of the test. So what this does is it calculates a number, which is a particular probability. It's going to be the probability of the testing criterion yielding data that are less compatible with the hypothesis than the data that you actually collected. So smaller values of this p-value indicate less coherence with the hypothesis, hence evidence against that hypothesis. Larger values indicate more compatibility of the data with the hypothesis. So here's a particular example, right? So in this particular case, we have data that we've collected that come out with a value of 4, and we're testing a particular hypothesis that the mean is 5 and that the standard deviation is 1. Using the ordering that I mentioned before, we find that we need to calculate the probability of getting data more extreme than or less compatible than the data of the value of 4 with the hypothesis. To do that, we calculate the total area under this curve, right? Because this probability density, right, we integrate it over a region to give us the total probability for the event, say from here to here is given by that blue region, and similarly for that blue region. These are each about 0.16, and so this yields a p-value of about 0.32. Indicates not perfect compatibility with the hypothesis, but not unreasonable either. In particular, right, we would expect that if the hypothesis were true, that we would get data at least this extreme or as incompatible with the hypothesis about 32% of the time. So the way Fisherian tests work is depicted in this sort of flow chart. We start with a testing criterion and a simple hypothesis. That is a very tiny laser pointer. We start with a testing criterion and a simple hypothesis. Now, when we put those two together, we get an ordering on the possible data. Now, the simple hypotheses provide probability distributions for the possible data. So when we combine those probability distributions with the ordering, with a particular data set, we can then get the p-values for those particular data sets. So it's important to note all the different components that fit together here for Fisherian testing. So the way Fisherian testing works, right, is one runs through this procedure, one calculates a value like this, and the smaller the p-value, right, for a particular test, the more evidence that we have against the hypothesis that we've tested. Of course, there are a lot of criticisms, and well-met criticisms, I think, right? So one is, how do you choose the testing criterion, right? I've given some plausible cases, very simple cases where we do that, but I haven't given a general procedure for doing that. Now, as it's stated, this testing procedure doesn't give us a means for providing evidence for hypotheses, just evidence against hypotheses. And we would also like to know, when is evidence strong enough to make an inference? When is the evidence strong enough for us to reject the hypothesis? Now, historically, Fisher developed many of these ideas, and Naiman and Pearson developed some of their work in response to that, trying in their own views to try to clarify what Fisher was doing. The direction that they took was rather different. So in brute outline, their approach to testing is, and this is a quite brute outline, right? Is divided into this sort of procedure. First, you take your space of simple hypotheses that you're considering, and you chop it into, partition it into two parts. Then you partition your possible data into two parts. If the data you receive lands in the first, you accept the first and reject the second. And analogously, if the data lands in the second, you accept the second and reject the first. Now, the reason why this is a really brute outline is that it doesn't tell you anything about how you're supposed to partition the data sets, how you're supposed to partition the hypotheses. So let's get into a little bit more detail about that. Okay. One thing to note is that unlike Fisherian testing, Neyman-Pearson testing requires consideration of more than one simple statistical hypothesis. So if you remember back when we were doing the Fisherian testing, the only thing that I needed was the one simple statistical hypothesis that gives me a probability distribution for the data. Then, given that, I can measure the evidence the data provide against that. Here, in order to go with this testing procedure, we need to consider a whole space of statistical hypotheses. Now, the way this is typically done is by looking at a common error typology with which many of you are familiar. So there are different things that can happen when you run a Neyman-Pearson test. One thing that can happen is you ended up making a decision, accepting the null and rejecting the alternative hypothesis. So the theta 0, sometimes called the null hypothesis. The alternative is the theta 1. When in fact it is true. And you can also reject it and accept the alternative when in fact the alternative is true. But you can also switch those around and make two types of errors. So one type of error is that when you reject the null hypothesis, right, when in fact it's true, or when you accept the null and reject the alternative when in fact the alternative is true. So there's a lot of different ways of setting down how Neyman-Pearson put their tests together. Let's just take one particular approach. In this case, let's just suppose that our theta 0 just consists of one single simple hypothesis. And what we're going to do is we're going to fix a number that we consider an acceptable type 1 error rate, known as alpha. Then, once we do that, they gave a prescription relative to some testing criterion of how to divide the space of data into two, so that you can specify the region that the data fall into when you want to reject the null hypothesis and when you want to accept the null hypothesis. In particular, the region where we're going to reject the null hypothesis is going to be the one where the p-value for the particular testing criterion that we use, when it's evaluated, right, at the simple statistical hypothesis that we're testing, falls below this alpha threshold. So the picture is familiar to you, right, because it's a very similar picture to what we saw before. In this particular case, I've picked once again this absolute value z test criterion, and I've picked the familiar value of 0.05 for alpha. What this does is this divides the possible data that we can receive in terms of its z-value score into these two regions. One is the light blue shaded region, and the other is the white region. If the data fall into the light blue shaded region, then we reject the hypothesis that we've tested, and if they fall into the white region, we don't reject, and instead we accept. Now, once we have that procedure, we have some ability to talk about which sort of tests we would like to use over others, which sort of testing criteria we want to use over others. And the reason for this, the reason why this is possible is that we're now considering a space of hypotheses. That provides us new resources that we didn't have in the Fisherian case. So the probability of a type 2 error, right, is going to be a function of the true simple hypothesis. It's going to be the probability of the true hypothesis such that the data falls into the acceptance region for the null hypothesis. Now we can define a quantity known as the power, which is just 1 minus this. I think the intuition that you should have for power is that the higher the power of a testing procedure, the more reliably that the testing criterion that it uses discriminates between the null hypothesis and the alternative, the true alternative. So Here's an example. In this particular case, the hypothesis space just consists of two elements. One element is that the mean of this distribution is 4, another is that it's 6.5. And here, the null hypothesis has been selected as 4, and the alternative is 6.5. And once again, we're using the absolute value of z as the testing criterion. So once again, if we set the type 1 error level at 0.05, we can calculate what the type 2 error rate will be. The type 2 error rate is going to be given by the area shaded here in blue. This is the probability that the data fall into the acceptance region, right, which is the region that's mostly white under the red curve, when it's actually the case that this alternative hypothesis is true. So that's why it's shaded under the blue curve rather than under the red curve. Okay, great. So this is how Neyman Pearson testing works. For those of you who are familiar with this, I'm very sorry to go over this once again. Now, there's also a lot of criticisms of this way of doing testing. So one is that it forces a dichotomous inference, right, about the null and the alternative hypothesis. And this is surely this is too coarse of a procedure for us. Surely there are certain circumstances where we want to hold our judgment in abeyance. We don't want to make a decision about which hypothesis to accept or which to reject. Now, another is that even though the power, right, of a test gives us some information about how to choose testing criteria, all else being equal, we like to choose testing criteria that have higher power because they allow us to discriminate between the hypotheses under test better. But the problem with power is that it's not a function of the data, right? It can't provide or quantify the evidence that particular data sets give to particular hypotheses, because it's a feature, a property of the testing procedure rather than the data set itself. Finally, another big problem is that although it may not have been evident, there's an asymmetric treatment of the null and alternative hypotheses. They are not treated on the same footing in how they are accepted or rejected. One really simple way to illustrate this is known as Lindley's paradox. So in this particular case, it's very similar to what we were considering before. We have two hypotheses in our simple hypotheses that we're considering. Again, situations where we have a mean of 3 and a mean of 7, but it turns out in this particular case that the data that we get has the value of 5. Now, if we use our usual testing procedure that we used before, setting our alpha level to 0.05 and so on and so forth, we see that if we had taken the hypothesis that the mean is 3 as the null hypothesis, it would lead us to reject it. However, if we had taken the null hypothesis as 7, it would lead us to reject it. So depending on which hypothesis we take as the null hypothesis and which we take as an alternative, will lead to a different inference. This seems like it's a big problem if you think that there is no, if that all hypotheses should be treated on a par with one another. And I think that they should. Okay, so in this next step, I want to outline how one might try to combine some of the benefits of these two while overcoming some of their difficulties. I should say that I haven't solved all of the problems yet. Like, I still think there's some open questions. I'm going to flag those and ask you for your opinion so you can see if you have any good ideas. Okay, so here's what I want to do. I want to be able to quantify evidence against and for hypotheses. Second is I want a symmetric treatment of all hypotheses, simple or composite. By symmetric here is I don't want to give certain hypotheses special status. I want the way that the procedure assigns confirmation of evidence or support to each one to be the same, regardless of the type of whether we want to designate one with a special name tag or not. That should matter. And finally, I don't want to force dichotomous inference. I think this is really a disaster. And I think everyone agrees it's a disaster. Okay, the result is going to be a 3-dimensional quantitative measure of evidence. What I mean by that is that there's going to be 3 different measures, quantitative measures, that are going to assign to how data gives support to hypotheses. In general, these three different numbers are going to be somewhat independent of one another. So the first dimension is something that we're already familiar with because it's basically the same as the idea that we saw in Fisherian testing. So this dimension I'm going to call fit, right? So let's consider some testing procedure and any composite statistical hypothesis. So here, this could be a trivially composite statistical hypothesis. And what I mean by that is it could be just a singleton, right? Or it could consist of many. So the intuition behind this criterion is that we want the data to be evidence relative to this testing procedure along this dimension for the hypothesis to the extent that if the hypothesis were true, then data that fit the hypothesis less would likely be observed. The reason why we want to think of it like that is that if it's likely that data that fit the hypothesis less are likely to be observed, that means that the data that we've received fit the hypothesis very, very well. It's simply going to be a generalization of the p-value of the statistic. The main difference here, you'll see, is that because H is composite rather than simple, we need some way of taking the p-values that we would assign to all of the different elements of H and putting them together. In this particular case, I'm taking the supremum. The reason why I'm taking the supremum has to do with the interpretation of composite hypotheses as disjunctions of simple statistical hypotheses. To say that we have support for, say, the truth of a long disjunction is to say, I think intuitively, that we have support for the truth of at least one of the disjuncts. And so we take the largest value, right, of the ones that are of the p-values that are in there. So that's the motivation for the supremum. There is another motivation that you can give for this, which is an analogy between a criterion that traditional epistemologists use in tracking theories or reliability theories of knowledge. I think I'm going to skip over that, but I'm welcome to come back to it if you want to talk about it. Okay, cool. So here is where the new action happens. So one of the things that struck me in thinking about these sorts of topics has to do with a certain sort of analogy. You'll note that the type 1 error is given by a particular formula, and the p-value of a testing criterion is given by a formula that are also very similar to one another. You'll notice here that the main difference between them is that the type 1 error rate has a particular constant that it sets as this lower bound. This is going to be a constant that's going to determine to make sure that the rejection regions in Neyman-Pearson testing are where you think that they're supposed to be. When we go to calculate a p-value, we use exactly the same procedure, except instead of this constant, we replace that constant with a data-dependent value. Right? We plug the data into the testing criteria, and we replace this constant with this value. So the idea here is that the p-value is like a data-dependent version of the type 1 error. The type 1 error is a procedural quantity. What I mean by that is that it's a property of a testing procedure rather than a property of any particular data set. We wouldn't say, for example, that the type 1 error rate gives us a measure of the evidence that the data provide against or for a hypothesis. But we would say that the p-value gives us a measure of evidence that the data provide against a hypothesis. So the thought here is do something similar with the power. So the power here, given as a similar sort of functional, the main difference between the type 1 error and the power has to do with a different a simple hypothesis that we're computing the probability over. Because remember, the power, which is 1 minus the type 2 error rate, that is a quantity which is concerned with the probability of getting data that is compatible with a hypothesis when that hypothesis is in fact not true. So the idea simply is to do the same thing with a new quantity that we did in going from type 1 error to the p-value. So that's what the severity is defined as. In this particular case, right, where we're considering one particular simple alternative hypothesis. So the idea here is that data is severe evidence, right, for some hypothesis theta, to the extent that if theta were not true, that is to say, if this alternative hypothesis, theta prime, were true, then data less fitting to theta would likely be observed, right? So remember, this ordering here, right, is the ordering of less fitting or less compatibility. So one thing for those of you who are familiar with the statistics literature, I want to observe is that severity is distinct from this other concept called post hoc power. In that, one replaces theta prime by a data-based estimate of that hypothesis, instead of replacing this particular constant here. So even though there might be a similar underlying motivation for this, I should say somewhat discredited concept, that severity is a different concept from it. Okay, so here's an example of how you might go about computing severity in these sorts of cases. Again, we have two simple statistical hypotheses, where we have a mean of 4, another we have a mean of 6.5, and we're using a test criterion of the z statistic again. We can calculate, right? So here we want to assign fit and severity scores to the hypothesis that the mean is 4. In this particular case, we can calculate the red area under the curve that gives the fit. Now, sev in this particular case, we have to look to the particular data that was collected. Right? Again, that's x equals 5 in this particular case, and calculate the area under the blue curve going to the left. The calculation here is exactly the same as in power, except that the location where you set your two areas to is determined by the data instead of being determined by the testing procedure. Entirely analogously to the way that the p-value is set from the data in comparison with the rejection regions for the type 1 error rate. So we can see that if we change the location of the data, that changes the calculation. So here, if we get data of 3, that the fits score increases quite a bit. And the severity also increases. You can see that the severity is very high here because there's so little area to the left here. The reason for this is that the data that we get here of 3 is so extraordinarily unlikely under the alternative hypothesis that if the alternative hypothesis were true, it's extremely unlikely that we would have gotten data of this sort. Okay, so there's another analogy that you can give between severity and these tracking criteria that epistemologists use. I'm going to skip over that again. Now, the formula that I gave before gives us a way of calculating severity when we're comparing 2 point hypotheses. Now, there's a big question about how do we generalize this to a case where the spacified simple hypothesis consists of more than 2 elements. So one natural way to do it, when the hypothesis that we want to assign a score to is a simple hypothesis, is just taking the infimum of the severity values. And the motivation for here, right, is that this is going to be the minimum power against all the different alternatives. Now, one of the interesting things about this is a very natural generalization, and it has an interesting implication. One implication is that in many testing procedures, no simple hypothesis is going to receive a high severity value. To see this, I think all you need to do is take a look at this particular curve here. I've drawn a bunch of curves, so it's the same sort of data situation as before, but now I've drawn a bunch of alternative hypotheses that are closer and closer to the one that we're testing. You can see that the blue area and the green area are getting closer and closer to the area under the red curve for the same regions. The closer and closer that they get, the severity level is going to go down and down and down and down, such that if you considered hypotheses that got arbitrarily close to 4, you would see that it goes down to its minimum value. The minimum value is going to be given essentially by the fit. So but that is actually a welcome result And the reason why is that we should think in situations like this that we're never going to be in a good position to have good evidence for a simple statistical hypothesis, right? We ought to think that in these sorts of situations that the types of hypotheses that we can have good evidence for are composite, perhaps narrow composite hypotheses that don't have a lot of elements in them, right? But not simple ones. So now we want to generalize this idea to assigning severity values for composite hypotheses, not just simple ones in comparison with ones that are composite. So here is we're reaching at the edge of the research project. And we're reaching the edge of the research project because there's a lot of moving parts and a lot of decisions that one could make, and it's not always obvious which direction to pick. So one is you'll notice that in the past the ordering, right, that we use is determined depends in general on the hypothesis that's being tested. So if the hypothesis is being tested as composite, there's a question about which ordering we should use on the data. That is to say, when we have a composite hypothesis, what is the right way of understanding how data are more or less compatible with that composite hypothesis? Another question is, should one take the infimum over all other simple hypotheses, as we did in this particular case, where we've replaced beta with some, which is a simple hypothesis, with some composite one? Right now, the procedure that seems to be working best for me is where we use the ordering that's given by the simple hypothesis that provides the best fit for the data. And that we shouldn't take the infimum over all other simple hypotheses, but only those sufficiently well-fitting. So it's a similar formula as before, except that there's some more complexity over what we take the infimum over. So, this is a typo, this should be H here. So we want to take the infimum, like before, ranging over the elements that are in the complement to the hypothesis that we're testing. But we only want to consider, yes.
Can you say what infimum is?
The minimum, essentially.
Okay.
Yep. If there's not a lower bound, then we have to pick an element which is the greatest lower bound. So, for example, if the numbers range, say, between 0 and 1, but not inclusive, then the infimum will be 0, even though 0 is not an element of that set. So it's the greatest lower bound of that element. But intuitively, you just think of it as the minimum. Okay, so here the theta with the hat on it is the simple hypothesis that has the best fit to the data. It's the best fitting simple hypothesis. The idea here is not to consider all the different hypotheses that we might imagine, right, that are in this space, but only to consider ones that are, as it were, sufficiently close to the best fitting one. The idea here is similar to an idea that some epistemologists use when they're thinking about evidence. When you want to have good evidence for something, right, you might want it to satisfy some sort of counterfactual condition, such that if things were slightly different, you would have gotten approximately the same sort of data, right? Now, if we imagine worlds that are very, very different, we can imagine worlds where we're deceiving by evil demons and so on, right? Those are far enough away from what we consider our best current estimate of what the world is that we don't want to consider those. There's an analogy also in certain statistical methods known as locally most powerful tests. We can talk about those in Q&A if you want to. So the reason why these sorts of things, why things get a lot more complicated at this point, has to do with the fact that once one generalizes to composite hypotheses, in situations with a bit more complexity, a lot of obvious choices end up not giving the answers that you would expect. So the third dimension that I want to mention is a looking ahead a bit to inference. So whenever we accept a statistical hypothesis, we want to reject its negation. Yet it turns out that high fit and high severity for a simple hypothesis don't necessarily entail that the negation of a hypothesis has no fit. it's still possible in certain circumstances for that to happen. So we can define a new quantity, the cofit of a hypothesis, that measures for a particular hypothesis how well fitting it is for its complement. To the extent that that it fits not so well, it gets a high cofit score. So we say that data, right, is cofit evidence for a hypothesis to the extent that if its complement were true, that is, that the hypothesis were false, we're considering, then data more fitting to that complement would likely be observed. Okay. Skip over the analogy between cofit and safety conditions. So the idea here is supposed to be that once we put these considerations together, we can calculate how data provide evidence for a statistical hypothesis to the extent that good testing criteria assign it a high fit, a high severity, and a high cofit. You might say that good testing criteria, right, make the data adherent, sensitive, and safe if you want to go by these analogies with epistemology. And data provide evidence against a statistical hypothesis in the same way that we expect from Fisherian testing, that it gets assigned a low fit value. Now, one of the things that, so this provides a quantitative measure of evidence for hypotheses. It treats all hypotheses on a par. There's no special treatment for hypotheses that are designated as null or not. And third, it doesn't tell you, it doesn't force you to make an inference about which hypotheses are correct or which hypotheses are incorrect. I do think that those elements have to be provided by something external. What are those things? Well, I think that's concerned with some of these open problems. I think that the answer is that the researchers' values, right, or values of the community have to play an important role for how the thresholds are set for inference. I don't yet have a story about how that's supposed to work. What about the values determines the thresholds? In particular, I would like it to be the case that these different measures of evidence and the thresholds interface with some of the machinery from decision theory about that. I don't yet know how to do that yet. I would like to. Maybe you can tell me. I'm going to skip over this. Here's what I think is like the big issue. How do you select the test criterion? I haven't said anything about that. In classical statistical testing, there are certain circumstances where you can prove certain optimality results. You set certain criteria for test and you prove that there exists an optimal test along those criteria. I don't yet know how to transfer those ideas to this framework yet. Some of these concepts involve ideas about the efficiency of a test, monotonicity of a test, the unbiasedness of a test. And if there's no reasonably objective standard for choosing among different testing criteria, can we at least bound the variability of the evidence that these different estimates provide? That would show that even if there is not a reason for selecting one particular testing criteria, if we can bound the acceptable testing criteria and show that they provide similar measures of evidence for and against hypotheses, I think that would be an interesting accomplishment. So I think I'm just about out of time, so I'll stop there and thank you for your very kind attention.
We'll take a 2-minute break and then we'll have time for questions. Oh, you can like get in?
3 weeks ago, and it's just not What's that?
Dangerous sports.
Yeah.
How much yesterday on skiing? No, it's not a ball, it's probably the general. I have an appointment tomorrow.